Hello and welcome. Today's webinar, Why Functional Safety, and then Understanding the IEC Functional Safety Standards. Now, the reason for this webinar is we do get a lot of questions, and it's always shocking to me for the reasons why people say why they don't need to do functional safety, or why even functional safety exists. And so today, I kind of wanted to go over and share you with a few examples as to why functional safety has almost become a household name, in the sense that 10 years ago, many people didn't even really know that functional safety was around, and now it's everywhere. And for those of you that are new, because I see a lot of people on here, we'll go ahead and explain what functional safety is as well in this webinar today. My name is Ted Stewart. I am the Program Development and Compliance Manager for exida. I have roughly 10 years of experience in the safety and high availability automation systems in manufacturing and lean process improvement. I used to work for Lockheed Martin in missiles and fire control as a test engineer. I worked for Harris Corporation in a wireless products group. And then now I'm here with exida. I've been with exida for about 5 years now, and it's fantastic. I do wear a lot of different hats. As you see there, I do manage the OEM certification division. I am the Deputy Quality Manager. I'm also the Director of the CFSP program. Before we get started here, I will go through a few introduction slides, but also note that there is a question bar over there. If you do have some questions, by all means, go ahead and type them in, and by the end of the presentation, I'll go ahead and get to those questions. Who are we? We like to put a few quick slides in here just to kind of do a quick overview of our company, and then we'll get to the meat of this webinar. We were founded in 1999 by several of the top reliability and safety experts, Dr. William Goebel and Mr. Reiner Faller. They saw a need in the marketplace, they got together, and they formed exida, and that was about, almost 20 years ago now. You'll see there on that map, it's pretty fun to watch. It looks like a little red dot. It's going to keep poking up every year. We have a new location. We just had somebody now who's a partner of ours out in Australia. Very excited. There's a lot going on there. And we're also hiring in the UK as well. So a lot of exciting times right now for us. Now, exida, we're involved with the complete supply chain of functional safety. You know, in many different industry sectors, we do work anywhere from the original equipment manufacturers who, perform that product certifications, and then all the way to their customers who are the end users that actually use those products. The things that we have gotten ourselves involved with, and it took over time, is now we provide not only product certification or consulting, we do software tools, we'll do training, we'll do procedures related to functional safety, related to security, and even reliability. Here's a snapshot of our product and suite of services that we do offer. I'll do one quick slide on each one of these topics. It's going to be in consulting, engineering tools, product certification, training, the reference material, and then, of course, personnel certification. In our consulting and engineering services, our main goal is to have the people, the personnel, to help achieve whatever goal you're looking for in functional safety, in alarm management, or even cybersecurity, whether it's design, implementation, operation and maintenance of those automation systems. And like you say here, I touch on functional safety, process safety, alarm management, and even cybersecurity. Tools. I know just last week I was telling a story. We were over in the UK. We were given a seminar over there. And it was kind of interesting because, we bring our tools with us. So if someone wants to play with some of the software, they can. And I never, when I first started working with this company, took advantage of that. And I was one of those guys that, I'll just do it manually. I got the calculations. I know them all. I'll just figure them out myself. Well, wow. When you start working with PHAs, LOPAs, SIL selection, if you're doing SIL verifications, and you got like 100 SIFs to do, it is so nice to have a tool that will just help you out, make sure your eyes don't get crossed, and it basically does the work for you. So I'm a huge supporter now in engineering tools. exida certification, this is something I spend most of my time in, whether it's 61508 certification, 61511 certification, we can do automotive in ISO 26262, we'll do cybersecurity, machine safety, and of course certifications with personnel as well. And that's the reason why we bring up personnel more and more is because now in the new standard of 61511, personnel certification is now becoming more of a requirement. And that's something that was not in the past, where now they're saying, look, okay, we understand you're going to certify your process, you're going to bring these products in that are already certified. But what happens if the people that are using these products and looking at these procedures are incompetent, right? So that is a missing key, and the people who were on the 61511 committee, they did a fantastic job putting in personnel competency. We at Exeter, we were not involved with the standards or those committees, so we're happy that they're lining up perfectly with the work that we're performing, and that's personnel, like we just spoke about. All right, let's get into the meat of today's presentation. Thank you so much again for attending. So functional safety, it has become a greater awareness in the last decade, but we are still seeing companies being more reactive instead of proactive. So what do I mean by that? I mean by, when an accident occurs at, let's just say at a reputable company site, whatever the industry, oil and gas, automotive, nuclear, that industry then, after an accident, they start rethinking, what about functional safety, and what should we implement now that something has happened? We need to fix something. And of course, this is human nature. This is a human reaction, which is unfortunate because when it wanes over time, a lot of people don't do anything until another incident strikes, and all of a sudden, boom, we take action and we make things right. Now, there's a debate that only if the accident could have happened at a sparsely populated or, a desolated place, then human loss of that life could have been prevented. But the hazards, following Murphy's Law, they have a tendency to crop up at the wrong place, at every inappropriate time. But as human beings, it's true that we cannot outwit each and every possibility that can hurt us. But what we can do is, from learning from those mistakes, not only the mistakes you make, but the ones that everyone makes, if we could take all of those, collectively brainstorm on determining the root cause, this can now make us less prone to those fatal accidents and achieve a safer workplace, a safer environment, and a safer life. All right, so why isn't functional safety everywhere? And and it's becoming more common. It's becoming more into everyone's processes. Because when you start thinking about functional safety, what it could do to prevent and what could help, we're talking big things here, like fatality or loss of human life, monetary loss in terms of damaged equipment and loss of production, environmental impact, and that could be anything with the pollution of natural resources, the reversible or non-reversible impact on wild and marine life. You have production downtime, and so doing functional safety, is it worth the risk? Now, of course, you can't put a price on a life. You could put a price on production downtime. That's pretty easy. But why do people decide, oh man, it's just not in my budget this year, or what, we've been just running around the clock. I'm underwater as it is. We just don't have the time, or well, we got all these projects going on, and we just don't have the personnel right now to do this work. And you just have to ask yourself, what is the chance? What is the risk? And run your statistics. Is it important to you? Well, there's three. I only did three, right? Because it's not even fun talking about these events, but just to give a little background, if you need the resources to where I got my information, I'd be more than happy to if you send me an email. But, so let's talk about first Deepwater Horizon oil spill. I picked three, and I'm going to talk a little bit about each one, just so those that are on this webinar today, if they don't have a full understanding, they can see what occurred and then how they really can be prevented. Now, according to BP's September 2010 report, this accident actually started with a well integrity failure. This was followed by a loss of control of this pressure of the fluid in the well. So there's a blowout preventer, which basically is a device which should automatically seal the well in the event of a loss of control. But this actually failed to engage. And the hydrocarbons, right, they shot up the well at an uncontrollable rate. It ignited, causing a series of explosions on that rig. Now, were BP's safety standards adequate? Now, that's not an opinion of mine, but according to the final report, they said no. And what they said, and they quote, that this disaster was preventable if existing progressive guidelines and practices have been followed. But BP did not possess a functional safety culture. For me, that one line just hit home because, this is why I go to work every day. This is what, I want to do is I want to try and help people. I want to make the world a safer place. And seeing that they outlined what I directly am helping people do, that really just hit home. And so that makes you, work that a little bit more faster, a little bit harder to help people realize that these things can be prevented. Let's look at the next one, the Texas City refinery explosion. Back in 2005, here's how this one happened. So after works had been completed on the refinite splitter, consideration was given to the impeding startup of the plant. Okay, so one of the primary safety critical steps in this pre-startup process was the use of the BP pre-startup safety review, which is a PSSR procedure. The purpose of the review was to ensure the complete and thorough technical checks were carried out and that all non-essential personnel were clear during that startup operation. And once completed, this PSSR would be signed off by the refinery operations. It'd be signed off by safety managers, authorizing that the startup work, but authorizing the startup work. But this safety procedure was never completed. In addition, there were a number of safety issues with items of safety critical equipment, which had not even been resolved prior to starting up and commencing. And some of the items that weren't even looked at were there was an inoperable pressure control valve. There's a defective high-level alarm in the splitter tower, a defective sight glass used to indicate fluid levels at the base of that splitter tower, and then the vital splitter tower level transmitter hadn't even been calibrated. Right, so there was a lot of things going on, and of course with 10 years of hindsight, what did we learn? Well, this particular process safety incident was really not even a momentary lapse in a facility that otherwise, had a clean history with a strong safety compliance and a long-standing safety culture. It was the complete opposite. This refinery had experienced 23 fatalities over the previous 30 years, including 3 in 2004 alone. That's just 1 year before the Texas City refinery explosion. And this wasn't even the first time that this specific safety compliance lapse had occurred with this very equipment. There had been 8 serious releases of flammable material out of that stack in the previous years before 2005, but nobody had ever investigated the causes. And moreover, such overfilling incidences in the distillation column had happened in other refineries. An investigation cited in industry literature stressed the importance of accurate level measurements as part of the overall safety risk management system. So it's kind of shocking when you look into things and it's like, wow, you mean this happened before and this could have been prevented? And it's just people get so wrapped up with time and budget and look, if we shut this plant, we lose X amount of dollars. But if you look in the screen, I mean, even the Deepwater Horizon, that cost them $4.5 billion. And, in Texas City, $21 million because of their negligence. And then the last one we'll talk about, we can keep moving on here, was the Piper Alpha. That was over there by Scotland. This was an older one in 1988, but it's one of the first really, largest oil platform accidents that were out there. And so here's what happened here is the original modules on that structure, they were carefully located, right? They were doing everything right. They had the staff quarters kept way away from the most dangerous production parts of the platform. But here's what happened. The safety feature was diluted when the gas compression units were installed right next to the central control room. And then further dangers arose when the Occidental decided to keep the platform, which produces the oil and gas. They set it and kept running it while construction, maintenance, and upgrade was in the works, right? And so here's what happened. When they kept running it, there was a lack of communication at the shift change, which meant the staff wasn't even aware, and they didn't know that they couldn't use a key. They couldn't use a key piece of the pipework, which had been only temporarily sealed off and there was no safety valve. What happened? Winds came around, gas leaked out and ignited, and while those firewalls that usually would resist the fire in the platform, it failed to cope with the ensuing gas explosion. And this was absolutely a horrendous, horrendous catastrophe. All right. Oh, I got to get away from that because it's hard to read those things. And so let's talk about functional safety and what we can do about it. And I want you to note that here's what a SIF is. It's going to have to include an element of detection, a decision, and there's going to be an action to achieve or maintain this safe or mitigated state, right? And sure, the action's important, but make sure it's a safe action, right? Because we've been to some sites where it's like, yeah, we got the detection, we get the decision, and it does something. But we got to make sure it fails, if it were to fail, in a safer state, right? So here are a couple of examples. You have the first one on, here's one. On detecting high temperature, it prevents the column rupture from shutting off steam flow to the reboiler. That makes sense, right? You have your detection, your decision, and there's an action. On detecting a high pressure, you prevent the tank rupture by opening a valve, right? There's your action, to relieve the system. Another one, on detecting high level, you open the drain valve to direct excess liquids to the waste pump to reduce environmental damage. Well, that's great. Now, what about this last one? On detecting a fire, it issues an alarm to minimize damage and possible injury. Yeah, there's detection, there's a decision, and there's an action, but this isn't a complete SIF because it doesn't achieve a safe state. It really just mitigates. And so final actions must be included beyond just the alarm saying, hey, there's something going on. So what is functional safety and who should be using it? Well, functional safety is the adoption of two different standards. You have IEC 61508 and IEC 61511. And then I put a little blurb in here because it comes up quite frequently, and it does include mechanical devices, even though these standards are all about electronics. Now, functional safety standards, it addresses the life cycle, systematic faults, and random faults. The key is in the documentation. I'm gonna talk about documentation more and more because that is one of the areas that we're noticing is lacking when people are interested in functional safety. You can read here information that's supplied to end users. We'll be talking about what are customers doing, critical issues, importance of data integrity. We'll talk about product certification, and of course, roles and responsibilities. Now that we're starting to build a framework here, let's go into what is the goal of functional safety, and then we'll just step through for end users and for manufacturers the different process here. So the goal of functional safety is the automatic safety function will perform the intended function correctly, or the system will fail, but in a predictable, safe manner. All right, so just read that one more time so it sinks in. The automatic safety function will perform the intended function correctly, okay? Or what will happen if everything runs correctly? If it doesn't and it fails, it's going to fail in a predictable manner. Now, working groups and national standard bodies from around the globe have been involved in the process of bringing this 61508 standard together. And there are different standards out there. I'll go from right to left. I know that's, I'll go from left to right. The first one is the EWICS, EWICS, right? It's the European Workshop of Industrial Control, computer safety. That's what it is. The next one you have is HSE, right? They're the United Health and the UK Health and Safety Executives. They have a guideline on programmable electronic systems. Real quick thing on them, we just actually visited them last week because we're always trying to visit the different bodies of the regulatories to just make sure that we're staying on target, we're keeping up the track, and it was a very fun meeting. Phenomenal people. When we sat down with them, we addressed our concerns, they addressed their concerns, and they were almost identical in what we were looking at. Whether it was, hey, we see some gaps in documentations, hey, we see some gaps in the operation and maintenance phase of the life cycle. And it was so refreshing to see that the work that X is doing and the work that HSE is doing completely in parallel, we were both on the same track, and it was really cool to see. Another one is the ISA 84 committee. This is the application of safety instrumented systems for the process industry. That group's out of America. And then you have two German standards here. You have the DINV 19250. This is the functional safety aspects to be considered for measurement and control equipment. And then the DINV VDE 0801. This is the principles for computers and safety-related systems. So with all of these, you combine them all together, and then that's how we came out with IEC 61508. And in summary from that, now because you have all these groups together, what did we get out of it? Well, this standard applies to the automatic protection systems, right, for EEPE. And I'll explain what EEPE is in the next slide. It provides measures of protection against those random failures and systematic design failures. It can be applied to project level work. So those are more bespoke turnkey systems. And it can also be applied to the product level work, which is those off-the-shelf products that you have applied in many applications. Now, basic safety standard upon which other functional safety standards get developed. Now, from this, it's going to target your suppliers, and it's anyone making that safety-related electrical, electronic, or programmable electronic products for the use by other OEMs. These are the ones that need to follow this standard, right? So it's those manufacturers, those OEMs. These are the ones that will use this standard to get product certified, to get assessed to. Of this standard, there's 4 normative parts. There's 3 guideline parts. This standard will define the concepts of safety integrity levels. It'll help show the safety life cycle. And of course, there's certification, which is optional. But assessment, though, against the requirements of 61508 is not optional. And this is when a third-party certification is valued by the end users, so that there's no bias when the work is being done. Now, the IEC 61508 standard, it started, as a non-governmental industry standard, and it has grown steadily in its use and its enforcement. And currently, its level of use and application is so prevalent that it can be dangerous for an organization to ignore the standard's recommendations. And as most societies have become more risk-averse, compliance with this standard is becoming all but mandatory in most parts of the industrial world. And that's really exciting to see that it's starting to catch on, but it's because people are seeing that it's making a difference in their equipment, in their process, and even, in their plan as a whole. Speaking of EE and PE, I wanted to just throw this slide in here because sometimes it's not common knowledge. You take things for granted. So the E and EEPE of the 61508 standard is electrical. Then you have the electronic, and then you have the programmable electronic. And this is when that question comes up, and they say, well, look, hey, Ted, I see what the standard says. I see EEPE, but I don't see an M. Where are those mechanical products? We just tell people, hey, look, we'll Google it, and when you Google looking for mechanical products for IEC 61508, the first search that we came up with was the IEC standard. And when you go into it, you come to a screen like this. It tells you the scope, and then when you zoom in, now you have this. Now you have the safety critical mechanical devices, and it shows that it must be included. And even though you may not have these electrical portions, if you have a valve or an actuator, you have the standard. You do have to meet the other portions of that standard, because when you go through the analysis, there's going to be some sections that are NA because you don't have that FPGA, or you don't have a smart device within yours. And if you look at that third paragraph specifically, now I'll just read the first sentence there, and it says, even during later phases, such as the realization, specific functional safety requirements apply directly to non-EEPE devices, such as mechanical components, as well as EEPE devices, right? So that's right there. That's specifically out of the standard, and it's thrown in there to make sure that people are now using this standard for mechanical devices. And we have always been doing this, but we've always were asked, where is it in the standard? And so we kind of just wanted to point out to make sure that people could see it. All right, I hope everyone's following along. We're just basically building up functional safety and kind of then dissecting it so everyone can understand the concepts. And if you have any kind of questions like I said, please feel free to go ahead and ask a question. So the standards, like we said, it started with the IEC 61508, and then there was more of a need once that standard was developed, because you have people in other industries that don't need to follow that specific standard. Sure, it's the umbrella standard, it's the main standard, but then it breaks out. Let's say you're in the nuclear sector. You want to use IEC 61513. Let's say you're in the machinery sector. That's IEC 62061. Process industry sector, most of you end users that are on this webinar today, IEC 61511, which you're very familiar with. So now what are customers doing? All right. We'll talk about the 61511 standard, we'll talk about the safety integrity levels, and we'll also talk about the safety life cycle. So what is the 61511 standard, right? We talked a little bit about 61508. Now we're going to switch into 61511 a little bit. Now this one is user-focused. It does not assign responsibilities that must be done for any given project, right? So you're actually going to see a functional safety management plan. That's what that's for, right? There's no detailed requirements for embedded software or high-level languages, right, like C or C++. Guess what they want you to do there for 61511? Hey, they want you to go reference 61508 if you're going to talk about those things. And then they use the same life cycle and SIL concepts as 61508, but it's now gauged toward the process safety language. So now let's talk quickly about what is safety integrity level. What is SIL? What is that SIL thing, right? Now in 61511, it only defines requirements for SIL 1 to SIL 3, and it is expected that SIL 3 will be the maximum level in a process sector, except, of course, nuclear. And for SIL 4, IEC 61511 refers to the users back to the detail in 61508. And what I was told, what I'm actually looking in from this morning, is they're even saying that SIL 4 for railroad could be applicable. I've always questioned SIL 4 only because I always ask people, do you really need all those requirements met, and are you over designing something? And that's when you start looking into your risk reduction factor and your PFD average and things like that. So let's say for this sake, we're going SIL 1 to SIL 3, and that's what we're looking at. Bridge to safety. This is kind of one of my favorite slides. I love visual pictures, and it helps me put everything together. So let's pretend, all right? Let's say that you're new to IEC 61511, all right? And you like to be evaluated to the standard. And you have these IEC 61511's pillars holding up both sides of the bridge, right? On the left and on the right. And you need to cross the bridge or construct the bridge to complete the evaluation. Now, as you go through the process of each requirement, right? Hey, I'm at general, now I'm at safety management, safety life cycle, and boom, here's another pillar. I'm at the planning pillar, right? And then you're going to just keep going along the path, right? As you go and you complete, you're actually making steps to complete this bridge. Now, if any time, though, you skip or you fail to build a portion of that bridge, the entire structure can't hold itself up. And it's so true, because this is the same thing with the IEC 61511 standard. If you only do 90%, which people are like, hey, that's an A when I went to school. You do 90% of functional safety, your functional safety bridge will still fall down. Here in front of you, we're gonna talk about briefly both of the safety life cycles for 61511 and 61508. Let's first touch 61511, since that's kind of the mindset that we're in right now. As you see, there are 3 different phases. You have the analysis phase, the realization phase, and the operation phase, and we'll touch about each one. Okay, let's start off with the analysis phase. Now, in safety instrumented systems, these are designed to automatically protect an industrial process. The steps required to do this cannot begin until the conceptual design for a process is complete. All right? So at that point, the process is examined for its potential hazards. The risk of each hazard is assessed by estimating the likelihood, or the frequency of the occurrence and consequence magnitude if it does occur. Now, for those risks that need to be reduced, safety requirements have to be created. And often the needed safety can be achieved without a safety instrumented system. Now, for the places where you do need an SIS, which is going to be your best solution, a risk reduction target is defined with a safety integrity level, and now a description of that needed safety function, along with all the other important information, which includes the SIL, is documented in your living document, in that SRS, that safety requirement specification. And I'll go to the next slide, because here's what we're talking about when you need to select the safety integrity level. For those hazards where this SIS is required to achieve that necessary risk reduction, an order of magnitude is called a safety integrity level, right? This is what is selected to specify that risk reduction target. You select your SIL when you find out how much risk you actually need, right? So this way you don't underestimate or overestimate, or design, I should even say is a better word, your system, right? This will let you know, okay, here's what I need, here's the reduction I need. Now, where can I fall to get the required SIL level, or for whatever system I'm trying to build? So when you're doing your calculations, your main objective is to specify the required risk reduction of the differences between existing and tolerable risk limits. And you can now see if your system, doesn't even need a SIL 3, or maybe it only needs a SIL 2 for the requirements that you're looking for. And you can then compare the process risk against the tolerable risk. And you can use decision guidelines to select required risk reduction. And of course, finally, which most importantly for me, is you want to document the selection process. Documentation is key to both of the standards. Now, let's move into the realization phase. The realization phase begins with conceptual design of this safety instrument system, and it's based on your SRS, your safety requirements specification. And the desired technology is chosen from equipment like sensors and logic solver and final elements. And you'll see here, just so you know how this chart works, I should have done this on the last phase, but the very left part, these are all the documents that you're gathering, right? You have to collect this information. Then the middle is the requirements you're going to have to meet, and then the right side is where it spits out all the different types of reports. So that's kind of how you're seeing it. So when you need your manufacturer safety manual, you're gathering the information. You use it for your SIF conceptual design, where you select your technology. You use it for SIF conceptual design, where you select your architecture, and then it spits out your equipment justification report, right? So that's kind of how this phase works. Now, let's go back, because that desired technology that you're choosing, those logic solvers, those sensors, those final elements, once this equipment or this technology is chosen, often redundant device configurations or architectures are then selected based on the experience of the SIS design. And there's several different architectures that can be used depending on the performance of the individual components and the needs of that system, right? So they'll commonly have names like, you'll see something like 1001, which is 1 out of 1, or 1 out of 2, or 2 out of 3, and 1 out of 2D. And so to just let you know what that means, so if I say, hey, I need a 2 out of 3, what does that mean? Well, this configuration means that there's 3 elements, right? They're present, and 2 of those 3 devices must indicate a trip in order for that trip to be signaled. All right, now we're into the operation and maintenance phase. And I always say this is the forgotten phase because it's so true. Once people get things moving, they get their product out the door, they're working, hey, it's in production, we did all this great work beforehand. Well, you know what, maybe I don't need a proof test so much. Or, you know what, it'll be fine. Nothing ever fails anyways. Man. This is one thing we're working on, and a lot of people out there are still working on the operation phase. But this phase of the safety lifecycle, it begins with validation of that design, right? And now this validation must answer numerous questions, and I have 5 or 6 here that I'll read out. So the first one would be something like, does the system solve the problems identified during that hazard analysis, or have all necessary design steps been carried out successfully? What about, has the design met the target SIL for each safety instrumented function? Or what about, have the maintenance procedures been created and verified? Is there a management of change procedure in place, and and are operators and maintenance personnel qualified and trained? Which is Once again, I threw that question in there because why? 61511 is becoming more and more robust on personnel certification. And so the answers to these questions, they must be acceptable answers before proceeding into startup and operation. And that's critical because of, like I showed those examples previously where things bad happened because they went a little too quick and they got a little anxious and skipped steps, and that functional safety bridge crashed, right? Now, as you go through the safety life cycle, what you're really doing is you're designing strengths against random and systematic failures. And I don't care what you call these types of failures because they're all failures, right? And so why does and on the flip side, sir, you got all this information, you got your data collecting, you're looking at all your procedures, and why does this data integrity really matter? And then there's this comparison of data sources, and oh yeah, you know what? I have this valve and it's 5 magnitudes better than any other valve from the market. It's got to be the best one. Let's use this one. You got to start asking yourself, is it too good to be true? Aren't valves pretty much, now some valve manufacturers will argue with me, but aren't they at least similar? Yeah, some have some very neat designs inside. They do make themselves different from the market. But 5 orders of magnitude different? What about your product stewardship? Or, what about that legal responsibility? Because remember, bad data can affect so much. It can hurt that bridge of yours because you can have the optimistic data. It leads to those unsafe designs. And if you're using bad data to do your calculations, then some of the calculations effort that you put into making that system safe will no longer have the effect that you wanted, because optimistic data can create an insufficiency in redundancy. Your proof test can be incorrect. And what does that mean? That means, look, because you think you have something that never ever fails, you figure, I can have a one valve in the SIL 3 application, right? I don't need redundancy. Or, hey, my proof tests, I only have to do it once every 6 years or once every 7 years even, because why? This valve, it's never failed. That's what at least the numbers are showing me. And so really the main objective is that you could not reach the required risk reduction needed to operate a safe plant if you're not using realistic data. Looking at the definitions of what bad means, right? Because we're using this term. Well, in the dictionary, it says failing to reach an acceptable standard, which is, in other words, poor or a bad repair for a job. A bad repair job. What exida defines bad as, if we put it back into functional safety, it's data that leads to unrealistic, often dangerous designs. So when you're looking at data and you're like, hey Ted, this is all great. Of course, I don't want to use something that's too optimistic. I don't want to design something incorrectly because we just spent so much money, making the perfect system. Well, how do I know if these manufacturers are giving me failure rates that are accurate and things that I can use? Well, there's now a site, make it a little bit easier with a range, right? So if you go to silsafedata.com, let's just pick that very first one. It's an actuator, a pneumatic piston. It's a spring return. It has a lower bound of 190 fits and an upper bound of 1,000 fits. So now if you have this actuator and you get a certificate and it's a pneumatic piston with a spring return and it says 5 fits on it, oh my God, you need to at least, hey, you know what, if you want to say it's accurate, that's great, but at least ask that manufacturer, how did they determine their number, and at least question it. If it falls within these bounds, then you say, you know what, this is good information, I got it. This at least looks realistic. All right. It says, yeah, some products will fall. If they fall outside of these ranges, find out why. Okay, and make sure that work was done correctly. Now, even with bad data, there's different definitions for risk, and risk varies with however you use that term. And here's 2 drastically different examples, but at least you can get that point across and drive it home. Where, let's say you have a marketing brochure. And you can say, we make very high quality stuff. It never fails. Very exciting. Big font, thick font. Huge. Now here's the thing: your risk, it's low, right? Your reputation, it might suffer, right, if you're not telling the truth because of these exaggerated claims. But you're not hurting anyone. You're not killing anybody. However, let's take into a safety aspect where you have a safety reliability calculation. And here's a statement that says, look, the math shows you don't need redundancy and never need to test the function. This is a big problem. We're seeing, believe it or not, we see people do this. This is a very high risk, and there is a potential for loss of life due to that under-designing of that safety function. And it's a real concern, and it's out there. So that's why we keep talking about it. So finally, product certification. Now we've kind of went through the life cycle of 61511. Basically, your 61508 life cycle is essentially the same, with the fact that it's slightly different because this life cycle is now based on product and not on the process, all right? When you look into 61508 and you go through the process for manufacturers, or just let's say for equipment, there's two fundamental concepts, right? You have the safety life cycle, which is your detailed engineering process, right? Your systematic faults, your design mistakes. Then you have the probabilistic performance-based system design, right? Hardware reliability, which are what? Those are your random failures. Now let's kind of talk about these failures just real briefly, because this question comes up every single day. What's systematic and what's random? And many believe that these definitions exist to category failures and that they're actually mutually exclusive groups, right? And so what are the different actions that you would take if something was systematic or something was random? Well, if it was random, you would count the failure and the failure rate for future PFD and PFH calculations, right? So it's factored into your number that helps with the end goal of, well, how many fits is this thing, right? Now, if it's systematic, guess what happens? There's an investigation. They source out the problem and they take action to prevent the future occurrence. Why? Because a systematic failure is one that can fail in a predictable manner, and you can simply get rid of that failure because there was something wrong in the procedure, or there was a bug in the software, and so you can fix that. But here's what we say at Exida. We say, look, I understand that there's a big discrepancy of what's random and what's systematic. Why don't we just count all failures, all right, and we put them all in the failure rates for the future PFD and PFH calculations? People say, whoa, 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 but then all of a sudden you're going to get these really pessimistic numbers and they're way too conservative. But hold on, right? So you get all your failures, right? Great, you have this big pile of failures. Now let's investigate the source of the problem for all the failures, and if practical, right, if you can find something, let's take action to prevent those future occurrences, because you have these failures in front of you, whether it's been from field return information or manufacturer warranty data, but you have these failures in front of you. Let's fix them. But if you never fix them, those failures are always going to occur. So why not take credit for, even if it's a systematic, right? And who knows if it's random or systematic, but that failure, when you take action and that failure goes away, now you can take that out of your PFD, PFH calculation, and you can move forward. All right? And so as you improve your process, let's say, hey, you get them reevaluated, and then all of a sudden your failure rates go down, everything gets better, and it's because you're improving your process, and we're not just hiding failures that should be actually counted. And here we go. So you've gone through the system. You've gone through IEC 61511, now you're going through 61508. You're now at the certificate portion, and the end result of the certification process is what? A certificate, right? It lists the SIL rating, it lists the failure rates on the back page, and a good certification assessment will demonstrate high design quality for that hardware, that software, and high manufacturing on itself. And of course, one of the bullet points I like to make is that a good certification assessment will check to see that the proper end user documentation is provided, right? So they're going to want to see all the information end users need in that safety manual, because if it's not in there, it's really not helping them, and they'll have to do more investigation. They're likely to miss something, so why not place all those requirements in your safety manual? And that's it. That was my webinar. If you have any questions, please go ahead and write them down here. I hope you found this information useful. It's something that comes up a lot. We have a lot of people asking us for, the understanding of 61508, 61511. A lot of people asking, well, why do I even need functional safety? So if you would like, please ask some questions. I'll go through a couple of slides. I have one question here asking about training. That's perfect because if you do need training, now these are just the closest dates, but really go to the training site there, exida.com training, if you need some, if you would like to see when things are available, if there's one in your area. If you don't see one in your area, give us an email at this one right here, academy@exida.com, and they'll get back to you and let you know where the next training is for your area. Any other questions? All right. Well, hey, it was a quiet group. Not a big deal. I hope you guys enjoyed it. We'll be posting the slides and this webinar on our YouTube channel, and everybody that attends this webinar will get these slides as well. So thank you so much. I really, really appreciate it. I hope you found it useful. Have a great day. Take care for now. And thank you very much. I appreciate it.